Alrighty, people, now that we've got all that annoying conceptual stuff out of the way, let's actually get towards something that will help you on the test. Actually, the conceptual stuff will help you on the test. It will just help you a little bit more indirectly. Now remember, logistical growth differs from simple exponential growth, because simple exponential growth is that the rate of change is proportional to the population. Logistical growth adds this factor, which is 1 minus the population over the carrying capacity. And if you're given something like this, and remember it has to be in this form, it can be transformed just by memorizing the formula. Carrying capacity over 1 plus a e to the negative kt, where a is m minus p naught over p naught. Okay, and of course this comes from plugging in the initial condition, and I could have shown you that, but it doesn't really matter. You can probably figure it out for yourself. But basically, this is initial population, and carrying capacity. So let's go ahead and look at an example problem. Okay. The growth rate of a population of squirrels in a newly established wildlife preserve is modeled by the differential equation dp dt is equal to 0.0006 p 240 minus p. Now, here's the thing. Notice that there is not a 1 right there. There's a 240 right there. Sorry about the shadow. I'm trying to get my calculator. Okay? So once we actually recognize this as being close to this form but not quite, we can go ahead and try and transform it. Okay, so we have dp dt is equal to, well, 0.006. Here's what you do. In order to get 1 minus p over m, I just need to factor out 240. And when I factor out 240, it's going to combine with this 0.006, and it's going to make 1.44 p, 1 minus p over 240. Okay? Now that is my differential equation. Okay? Now, it asks in part A, what is the carrying capacity, okay? What is the carrying capacity for squirrels in this wildlife preserve? Well, carrying capacity is obviously going to be this. It's going to be 240. Okay, so once you've transformed that equation, 240 is your answer to A. What is the squirrel population when the population is growing the fastest? This is an extremely important one, okay? Because of the way logistical curves are actually represented, okay? They always ask this question in one form or another. This is a logistical growth curve, okay? If this is 240, there is always an inflection point halfway up. That's it, okay? So if this is at 240, then at 120 squirrels, you have an inflection point. So what is the squirrel population when the population is growing the fastest? It's here. Because remember, the inflection point is where it's steepest, is where the rate of change is the greatest, because here the acceleration is positive. It's getting steeper, getting steeper, getting steeper, getting steeper, getting steeper, getting steeper, getting less steep, getting less steep, getting less steep, getting less steep. So the dividing line between getting steeper and getting less steep is the steepest, right? And therefore that is the point at which the population is growing the fastest. If you determine that inflection point, you can answer B and C. Okay, so the answer to B is 120. The answer to C, you just have to plug 120 in to here, or anyway, you can just plug it into the original equation, right? And so, to the original differential equation. Either form, it doesn't really matter. This helped you to see the carrying capacity, and therefore knowing half of that was going to be the point of inflection. So it doesn't really matter where you plug it in, because this original is the same as this, just in a different form. You're going to use your calculator probably anyway, so let's go ahead and use the form that we have. 120, and then 1 minus 120 over 240. So basically that's 1.44 times half of 120, and 1.44 times 60 is 86.4, okay? The rate of change of squirrels per year is 86.4 at that particular time, okay? Because P is measured in squirrels and T is measured in years. That's it. And they love to ask questions about that point of inflection. And like I said, all you have to know is that that point of inflection is halfway up from 0 to the carrying capacity. That's it. Okay. Let's go ahead and do another example. Alrighty. The spread of a disease through a community can be modeled with the logistical equation, and there it is. Now, notice they did not give you the differential equation. They actually gave you the function, okay? And so they actually gave you P of t is equal to m 1 plus a e to the negative kt. Now recognize the fact that they actually gave you a 1 right there, so you don't have to change the form at all. And so that tells me that m is 0.74, which means the spread of the disease has a maximum carrying capacity of 74% of the population, okay? I also know that A is equal to 34. So if I actually find the original population, I can actually work backwards to find that. Or actually, I can just do it from here. So if I have 34, remembering that A is equal to M minus P naught over P naught, this is basically a formula of 3 unknowns. If you know 2 of them, it winds up being 0.74 minus P naught over P naught, and that becomes 34 P naught is equal to 0.74 minus P naught. So 1.34 P naught is equal to 0.74. And then, of course, P naught is going to be 0.74 over 1.34. And of course, you can go ahead, 0.74 divided by 1.34, and you're going to get 0.5522, whatever. So 0.552 as an approximation, okay? Now, it doesn't ask for that, but it says what percentage of the people will not become infected. I mean, this was basically, this right here was just for fun, just because you can, right? And just because you want to be able to identify the components of that particular equation if you're asked for them. So you have M, you have A. I mean, you could have recognized K as 1/4, right? Because K is that negative coefficient right there in front of T. It says what percentage of the people in the community will not become infected? Well, if the carrying capacity is 74%, and on a long enough timeline you're going to get basically up to 74%, then 26% of the population will remain not infected, okay? On what day will the disease be spreading the fastest? Well, if you know the carrying capacity is 74, then you know that the point of inflection is going to be at P, or in this case, Y, is equal to 0.37. If the point of inflection is going to be at 0.37, okay, then what we need to do is we simply need to solve for T. You can say, okay, well, 0.37 is equal to 0.74 1 plus 34e to the negative 1/4 t. Yeah, sorry, I just can't, when I can replace them, I try to. You can go ahead and flip this over. Okay, so you have 1 over 0.37 is 1.34e, and I guess I'll just go back to decimals as much as it pains me. 0.74, so we can multiply both sides by 0.74, and that winds up being 2 is equal to 1 plus 34e to the negative 0.25t, and that's 1/34 is equal to e to the 0.25t. Take the natural log of both sides, and you have natural log of 1 over 34 is equal to the negative 1/4 t, and so I get negative 4 natural log of 1 over 34 is equal to t. So that actually should be what we're looking for. So let's go ahead and use our trusty calculator. So we have negative 4 natural log, and we'll go ahead and use this, 1 over 34, and there we go, 14. Okay. Now, it says where y is proportional, was the proportion of the people who are infected after t days. After 14 days, okay, you're going to reach half of the carrying capacity, okay, at 37% of the community being infected. Because like I said, the point of inflection, where the velocity, where the differential equation, where the derivative is always maximized, is always halfway up, excuse me, is always halfway up to the carrying capacity. And all I did was just take half of, I took half of the carrying capacity and basically set it as the output and solve for t. Okay, and therefore it just wound up being rather straightforward. After I did a little bit of algebra, I wound up here. Now notice this. This problem contains no calculus. It contains knowledge of calculus concepts, but there are actually no calculus procedures or methods. Okay? It helps to understand where this comes from and how it relates to the original differential equation, but you weren't asked to solve the differential equation. You were simply asked to recognize. You weren't asked to actually find the point of inflection by taking a second derivative and doing a second derivative sign chart, blah, blah, blah. You were asked to remember conceptually that on a logistical growth curve, the point of inflection is halfway up to the carrying capacity, and to acknowledge that. But despite the fact that there were calculus concepts here, there were no calculus methods in this entire problem. And that's kind of interesting. One of the things that's kind of bizarre about the differential equations chapter is the fact that there wind up being a lot of problems that are calculus conceptually, but not calculus methodologically. And that winds up, being, on the one hand, good, because I walk through the general form of the differential equation and how to find its solution, and of course all of that was really, really nasty in finding partial fractions and all sorts of fun stuff like that. But you're not actually asked to do that here. You're actually given the function, and given the function you're simply asked to identify from the formula certain pieces of information, and you're asked questions about them. That's it. Okay, let's do one more video. I have another example, and then perhaps I'll pull one in from a former AP question, and that will bring us to the close of logistical growth, and that'll be the end of the sections that you are required to know for this upcoming test. Okay, as always, please email me with any questions that you have. Bye.